So in this case, if r is greater than 1, then we see that then this is positive, and so if r if gamma is 1 pi, then r will be greater than 1, and this this entire thing 4r minus 1 times 2r will be positive. If gamma will be non 1 pi, then r equals 1. In that case, this is negative because this term drops out, and this is minus 2. So this result will be omega equals omega 1 plus omega 2 plus 4 times r minus 1 minus 2r, and this will be greater than or equal to 0 if gamma 1 pi. So for r equal to 2, this is 0, and for r greater than 2, this will be positive, and this is minus 2 if gamma is non 1 pi. Okay, which is basically r equals to 1. So even if gamma is 1 pi, any of gamma 1 or gamma 2 could be non 1 pi. So that is a possibility if the two separate parts of gamma 1, if so look at gamma 1 as a graph which has further subgraphs. So gamma 1 is of course a subgraph of gamma, but gamma 1 viewed as a separate graph can have subgraphs also. So those are further subgraphs. So those subgraphs could be such that gamma 1 is non 1 pi. So let us see that kind of a scenario. Even if gamma is 1 pi, any of gamma 1 and gamma 2 can be non 1 pi, and the way it can happen is that you separate out gamma 1, say gamma A, gamma B, such that they are connected by a single line. So this is your gamma 1, and then you have gamma 2 here. There are certain external lines. Here also there are certain external lines. Now there are number of internal lines connecting gamma 1 and gamma 2. If all those r number of, these are the r number of lines that I'm talking about, I have separated out gamma 1 into gamma 1, gamma A and gamma P, gamma B, which are connected by only one line. Now, if all these are internal lines, these are internal lines will be connected to any of gamma A or gamma B like this, then entire gamma is non 1 pi, because if you cut this line, then it will separate out. But among those r lines, if some of them are connected to gamma A and some of them are connected to gamma B, then the entire graph gamma is non 1 pi, is 1 pi. So we should have a scenario like this. So these are the r internal lines. So if r internal lines are distributed over gamma A and gamma B, and gamma A and gamma B are connected by a single line, then gamma can be 1 pi and gamma 1 is non 1 pi. So if that is the situation, then omega 1, so apply the same formula here, which we applied to gamma. Now you apply the same formula for gamma 1. then you would be writing as gamma 1 will be written as gamma A, omega A plus omega B minus 2 because it is connected by a single line. So this is the same formula with R equal to 1. So that means omega, the original superficial degree of divergence of the original graph gamma, will be omega A plus omega B plus plus the divergence of superficial degree of divergence for gamma 2 minus 2. So if it happens that this portion omega A plus omega 2 is 0 or 1, then total omega will be negative. Now, this sum of three terms can be 0 or 1. If individual terms are, you can manage to get 0 or 1 by individual term being 0 or 1, right? But 0 means super logarithmically divergent. So that means any of these omega A, omega B, and omega 2 can be greater than or equal to 0, while the total omega being negative. If that happens, then in that case, although omega is less than 0, which means the total gamma is superficially convergent, but gamma must have an actual divergence. So because because by the arrangements of subgraphs, it is possible that there are certain subgraphs which have positive superficial degree of divergence, but excuse me, because of their arrangements within the total graph, there are certain negative contributions which will offset the positive contribution coming from the subgraphs, as a result of which the total omega is negative, while some of the omegas of the subgraphs being 0 or positive. In that case, of course, we have total superficial degree of divergence to be negative, but there is a subgraph which has positive omega, because of which that portion will diverge. And so in that case, a superficial convergence, omega being negative, does not imply that the graph is actually convergent. So let's look at some example. So this is phi 4, phi to the 4 in d equals 4. So consider this diagram. And this is your total gamma. If we calculate the superficial degree of divergence of gamma, then we notice that this has total 1, 2, 3, 4, 5 loops, and therefore each loop will give you 4 power of momentum upstairs minus the number of propagators, and the propagators is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 propagators. So these are external lines which we cut. So there are 12 propagators, so 2 times 12, so that is minus 4. So that is superficially convergent. The entire graph gamma is superficially convergent. But now let's consider breaking the graph into subgraphs, and let's take this, and this is say gamma 1, and then you see gamma 1 is not 1 pi, because gamma 1 has further subgraphs, this one and this one, which are connected by only one line. Okay. So this is a further subgraph of gamma 1. So that you may call gamma A. Similarly, there are 4 corners. You have gamma B, then gamma C, and gamma D. So each one, pick any one of them, say gamma A, then calculate omega A. Omega A is the superficial degree of divergence of gamma A, which is 1 loop and 2 propagators. So 1 loop will be 4 minus 2 propagators is 2 times 2, which is 0. So it's logarithmically divergent. So this graph, each 4 portion, each corner is actually separately logarithmically divergent. However, the total superficial degree of divergence of the entire graph gamma is negative. So it's superficially convergent, but actually the graph has divergence. So what is the meaning of this? For every graph gamma, the UV divergence comes from the corresponding region of coincidence. Which is a subspace of R gamma, which is the total region of entire region of integration involving all loop momenta. So this is the entire region of integration involving all loop momenta of gamma. But when you consider a subgraph, for a subgraph, we have R gamma sub, which is a subspace of R gamma. R gamma sub is the entire region of integration involving a subset of momenta corresponding to the subgraph. And that a subgraph corresponds to a subset of loop momenta. So the entire graph gamma has a set of loop momenta, and the integration region for all of them is R gamma. Gamma sub, the subgraph has involves only a subset of those loop momenta, and the entire region of integration of those subset of loop momenta is the region R gamma sub. Now, when a subgraph is divergent, then it is a subspace of this. It's a coincidence region corresponding to this. Subgraph divergence will come from R gamma sub C, and that's a subspace of R gamma sub, and R gamma sub is a subspace of R gamma, the entire. And this is not equal to coincidence region of the entire graph R gamma, right? How do they differ? I mean, if I take a cartoon of a three-dimensional space, say like this. So this is if this three-dimensional space is R gamma, this one, then RC gamma or R gamma C is actually the diagonal in this three-dimensional space, which will take the component 3 component to be equal to same to K, and then you draw the diagonal and then take the diagonal and take the length K to infinity. So it is in this region. It is the three-dimensional. So if you project it on the two-dimensional space, it will come here. It is in that sense. So there's a perspective here. One has to get that perspective right. So it is this region that is R gamma sub C. On the other hand, if you have a subgraph which involves only a subset of which is a subset of momenta, which is this two-dimensional plane. So if you call it say X, Y, and Z. Or rather, I should call it say L1, L2, L3. Then L1, L2 is a two-dimensional subspace, and that if a subgraph corresponds to those that subspace, it's a cartoon, that's that subspace spanned by L1 and L2, then R gamma sub C, this one will be the diagonal on that two-dimensional plane. So you take these two same and then draw a diagonal which is restricted to the two-dimensional space. I mean, if you draw the okay, so it is a three-dimensional. The previous one is a three-dimensional diagonal. This is a two-dimensional diagonal, and it goes in a different direction. It is in that direction. If you go far away, then you reach the region R gamma sub C. So I should move it a little bit. So let me see. Some space. Okay, so these two regions are different. So what we saw just now is that if the graph is superficially convergent while there are subgraph divergences, it means that the divergence comes from this location of the total integration region, not this location of the total integration region. So so the statement is that omega gamma captures behavior of integration over region R gamma C, and that behavior in this case is convergent. If you go to that location, that region of the integration, then you will see, you don't see any divergence, rather it looks like a convergent contribution. However, omega gamma sub captures behavior of integration over region R gamma sub C, and this behavior is divergent, which is quite possible. This is what superficial about it. So Weinberg's theorem says gamma is truly convergent. The entire graph gamma is truly convergent if omega gamma is negative, and also omega gamma sub is negative for all possible gamma sub. So given any graph, one particle irreducible graph, say gamma, you calculate, for example, in this example, you calculate the omega for the entire gamma. It must be negative. That's a necessary condition, but that's not sufficient. You have to investigate in this graph. You have to investigate how many subgraphs are there. Look into the subgraphs and figure out and show that each subgraph also has omega negative. In this case, it is not, which is why it is divergent. But then only if you find the omega for all subgraphs, all possible subgraphs to be negative, then only that graph is truly convergent. Okay, that's the statement.